Hello. Okay, so let me get my PowerPoint ready. Okay. So welcome all to the tutorial today. So today's tutorial will be about the solution of homework 1. So I will first give a very brief idea of how each of the problem can be solved, and then we will make the the PowerPoint with more details after this tutorial, and then I will send it to you through the EE class system. Okay, so we have 5 questions altogether in homework 1. So in the first question, so we want to find how many ways are there that we can permute P balls that are red and then at most Q balls that are blue. Okay, so we have altogether exactly P red balls, but then in the permutation, we can have 0 ball in blue, 1 blue ball, 2 blue balls, up to Q blue balls. So how many ways are there? So actually in this problem, we have the solution for you in the question, but then, so in order to get a solution, you need to have an explanation. So how do you explain? So one idea is we can separate the total number of ways into different cases and then use rule of thumb to compute each of the case and add them up. So this is the answer that we obtain. So this is p factorial over p factorial and then p plus 1 factorial over p factorial 1 factorial. Actually, it is p choose p, and then this is p plus 1 choose p, and then it is p plus 2 choose p, and then up to p plus q choose p. So what does that mean? So we are having different cases to consider. We consider the number of blue balls to be 0, and then the number of blue balls to be 1, the number of blue balls to be 2, up to the number of blue balls to be q. So this one is the number of ways with 0 blue balls. This is the number of ways with exactly 1 blue ball. This is the number of ways with exactly 2 blue balls, etc., etc. So we will see that all these cases are counting different ways. So we just add them up, and then we don't need to worry we are missing any case or we are double counting any case. Okay, so this is the way. And then in part B, we want to simplify the answer of A and show that after simplification, this is the result that we have. So this can be done by using a direct application of the hockey stick identity we have introduced in the tutorial. But then a question here is, so can we get a direct proof, a direct combinatorial proof for the result of A? So it is not that difficult. So as long as you can see that this is the value of p plus q plus 1, choose p plus 1. So in that sense, so we may think of something like we are trying to permute p plus q plus 1 so items with p plus 1 of the same class, and then q of them are of the different class. So this is the idea of how we can do. So here, let us imagine that we have altogether p plus 1 plus q boxes. And then we are going to put exactly p plus 1 red balls into the box, and then q blue balls into these boxes, each box holding 1 ball. Okay, so after we put the balls, so what we are going to do, we are going to discard all the boxes up to the first one that contains a red ball. So after doing so, what does that mean? We will see that, so including the box that contains the red ball, the first red ball. So after discarding all the boxes, what do we get? We will get a particular permutation with exactly p red balls and then at most q blue balls. So in such a case, we will find that by doing this, we get a configuration with at most q blue balls and exactly p red balls. And on the other hand, if you have a configuration with exactly p red balls and then at most q blue balls, then we can reconstruct such a configuration here in this case. So what I mean here is that the number of ways that we want to count in part A is exactly the number of ways to put these balls into the boxes in this particular scenario. So that's why we can directly compute the result of A here by using this p plus q plus 1, choose p plus 1. Okay, so this is the answer of homework 1, Q1 part B. And then for C part, so C part here, we changed the problem a little bit. This time, the number of red balls is at most P red balls, and the number of blue balls is at most Q blue balls. So how do we find it? So we can actually repeat the same idea as part A and part B, because we now know that this is the case with exactly P red balls and at most Q blue balls. So in that case, we can construct the number of ways here by checking out the different case when P is equal to 0, P is equal to 1, when number of red balls is 0, number of red balls is 1, number of red balls is 2, and up to the case number of red balls is P. And then we will find that after doing so, then we will get the result that we want. So this is the idea. Okay? And then, so the next question. So for question 2, we want to use combinatorial argument to show this equality. 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial up to n times n factorial is exactly n plus 1 factorial minus 1. Okay, so the idea here is we are trying to give a story. So notice that when you are asked to prove something using combinatorial argument, you must give a story rather than you prove it by using algebra. So how do we show this? So how do we show this? Okay. So here, there's a typo here. So let me quickly correct it immediately, sorry, so that I can quickly correct. Sorry. So there's a typo here. Just to make sure that we are all okay with this. Okay, so let me show this. So let us imagine that we have n plus 1 distinct items, and then we want to make an arrangement of them. And then, so first of all, so there are all kinds of arrangement, right? So how many ways are there that we are holding? Okay, so we make sure that the item 1 is not at position 1. So how many cases are there? So we will see that the number of ways that item 1 is not at position 1 is, we have n choices for whatever to be put it at position 1, right? So in that case, for each of these n ways, we will find that the remaining parts we can arrange in any way that we want. So in that case, there are n times n factorial ways so that the first item is not located at the first position. Now, so this is counting some of the cases of the overall n plus 1 factorial arrangements. So what is not counted at this point is we are not counting the cases where 1, the item 1, is at position 1. Okay, so now for any of the remaining cases that we want to discuss, then we will assume now that 1 is now located at the first location. And then we continue to ask us the second question. How many ways are there such that 2 is not located at the second position? So in such a case, then we will find that there are n minus 1 choice for whatever to be put at location 2 now. And then for the remaining n minus 2 positions, we can do whatever we want. So the number of ways that 1 is at 1, but 2 is not at 2 is exactly equal to n minus 1 times n minus 1 factorial. So we can repeat these arguments again and again and again so that we will get something that is equal to the left-hand side. Now, all the left-hand side will be counting the cases where, so the last case here is 1 times 1 factorial. It corresponds to the case where 1, 2, 3 up to n minus 1, they are already at the at their corresponding position. But then we want to find out how many ways are there such that the nth item is not located at the position n. So there is one way, 1 factorial. So all this counting will just exclude exactly one case. This case is all the items, they are already sorted. The first one at the first location, the second one at the second location, and so on and so forth. So in that case, all together n plus 1 factorial, we are missing one case. So n plus 1 factorial minus the case that we miss will be equal to something on the left hand side. Now for this part, so as long as you can make up a story rather than prove it by using some kind of induction technique or whatever, then it will be fine. Otherwise, if you are not showing a story, then it is not a combinatorial proof. Okay, so this is the hint that I'm using to remind us what we are trying to count. We are counting the number of ways that the smallest k items are sorted and they are stored in the first k positions. So this is the basic idea. Okay, and then for this case, we are separating it into two cases. We are separating it such that the k plus 1th item is equal to is located at the k plus 1 position or not. Okay, so to do this, yeah, this is the proof that we are using. Now for part B, we want to show that any non-negative integer has a unique representation of the form, something like this, a1 times 1 factorial plus a2 times 2 factorial, and so on and so forth. Yeah, so this is an infinite series, okay, such that each of these integer ak, they are, yeah, each of these ai, they are integers, and then each of the value here is between 0 and k for all k. So for a1, you can choose 0 or 1. For a2, you can choose 0, 1, or 2. For a3, you can choose 0, 1, 2, or 3, and so on and so forth. So the basic idea is we are making use of this one. So when you have a1 set to be the largest value, a2 set to be the largest value, up to, let's say, an set to be the largest value n, and then all the remaining part, they are all 0, we will see that this will give us a value of n plus 1 factorial and then minus 1. And then we will see that, so here, this kind of problem, we want to show this by using the idea that we try to show that any such number will have at least one representation. So this is the existence. And then we also need to show that it is also unique because we want to show the uniqueness. Now, the existence, this time we can show it by using induction. So we will be showing that any number that is at most n plus 1 factorial minus 1, so less than, strictly less than n plus 1 factorial, can be represented using a particular way such that we are using only a1, a2 up to an. Okay. And then all the other cases, an plus 1, we just need to set them to be 0. So how do we show? Yeah, this can be shown by induction. So I will leave this for you. Okay. But then after we have shown this by induction, then what do we know? We know that altogether between 0 up to n plus 1 factorial, between 0 up to n plus 1 factorial minus 1, yeah, between 0 up to n plus 1 factorial minus 1, there are exactly n plus 1 factorial numbers. But on the other hand, we just show that if we want to represent a number between 0 up to n plus 1 factorial minus 1, we are going to use a1 up to the maximum value, a2 up to the maximum value, a3 up to the maximum value, up to an up to the maximum value. And how many cases are there? So there are going to be, there's something wrong. Yeah, so something wrong in my proof. But then exist. Yeah, once you have, let me see. So how many ways we have this one? So there are going to be n times, so there are going to be, no, that's still okay. So how many cases are there? So there are going to be n plus 1 choice for an, because an you can pick from 0, 1, 2, 3 up to n. So there are n plus 1 choice for n choice for an minus 1, and so on and so forth. So exactly there will be n plus 1 factorial choice. So what I'm claiming here is that because the sum here is equal to n plus 1 factorial minus 1, and then for any number between 0 to n plus 1 factorial minus 1, you can always find the representation in this way. So there are exactly one-to-one correspondence between a number and its representation. So that means that it must be a unique representation. So there's no way that we can find two of them with the same representation. Okay, so this is the basic idea. So you can have your own proof, but then this perhaps is a different way of showing uniqueness. Okay, for homework 1, question 3. So question 3 is we want to find out the total number of ways to create two groups. So let's say the two groups, one of them is G1 and then the other is G2. And let's say G1 has exactly m integers and G2 has exactly k integers, such that all the numbers in the group, they are distinct and they must be chosen from 1 to n. And then we want any integer in G1 must be greater than any integer in G2. Now, this one, although it looks complicated from the first glance, maybe you can show this by using the rule of sum, because you can separate the counting into different cases. But then a very easy observation shows that by choosing any n plus k integers, by choosing any n plus k distinct integers from 1 to n, we will see that the smallest k integers, you must put them into G2, and the largest remaining m integers, you must put them into G1. Otherwise, it doesn't satisfy the second requirement. All integers in G1 are larger than those in G2. Is that okay? So for any particular way of selecting n plus k integers, it corresponds to exactly one way of creating the group G1 and G2. So how many ways are there for this problem? It is exactly n choose n plus k. Is that okay? Yeah, for no matter which case that you have, it corresponds to a way of selecting the group G1 and G2. On the other hand, if you want to select a particular group G1 and G2, you just need to create a particular way of selecting n plus k distinct integers from n. So there is a one-to-one correspondence between the selection problem and the number of ways we want to do it. We want to do the counting here. So question 3 can be solved by using this observation. Okay, so how about question 4? Okay, so question 4 is actually a very easy problem. So we want to find how many 5-letter sequences that we can create such that each character that we need to select in the sequence is either A, B, C, or D. And then we don't want to see BAD to appear consecutively inside the sequence. So we don't want to have BAD as a substring. Okay, substring means contiguous characters. Okay, so this is not the same as subsequence. So subsequence may be not contiguous, but then substring, they are contiguous. Now, to do this, yeah, this is actually easy if you compute the problem using a different way. So we actually find out how many ways are there such that the 5-letter sequence contains BAD. And then if we can find out such a number, then we deduct on all the possible 5-letter sequence that we can create. So this is like we count those cases that we don't like, and then use the overall number of cases minus those that we don't want to count out what we want. So this is a similar question like how many ways that we can have a string such that it contains at least a 1. Okay, so instead of doing this, so we count the number of strings, number of let's say 10-digit number that doesn't have 1 inside. So by doing subtraction afterwards, then we get the desired result. So this is a very easy problem. So we can solve this by using the rule of difference. And finally, this is the last one. So the last one is a very interesting question. So let us say we are constructing an n-sided polygon. So it has n vertices. And then using this polygon, we are going to draw diagonals between any two non-adjacent vertex. And then we assume that this polygon is not that regular, it is quite skewed, so that any three diagonals do not meet at one point. But you will see that any two diagonals must meet at one point. And then we want to find out how many triangles can be made by the intersection points and the vertices. So for this one, yeah, actually, we have you can see a very nice tutorial from my previous tutor Simon from this OCW recording, but there is a hinted guide here for this question when we are designing this question. So we try to classify the triangles into different types. Okay. So we want to count how many triangles can be made such that the vertex of these triangles, they are original vertex of the polygon. So in that case, this number is easy because we can show that for any three selected vertex of the original polygon, yeah, then there will be diagonals, right? And then there will also be the edge of the polygon. So these diagonals and the edge together will form a triangle such that the vertices of this triangle are the original vertex in the polygon. So this is one type of triangle that we can count completely exactly. So there are how many of them? There are n choose 3 of them. Okay. Now let's also look at another extreme case. So another extreme case is we want to count how many triangles can be made such that all the vertices of this triangle, they are intersection points of the diagonals. So they are interior intersection points of the diagonals. Now for this kind of triangle, we must see that we need to use 3 diagonals to define the triangle. So let me draw a figure for you so that we can see this more clearly. So in particular, so if I want to have diagonals such that we want to have, let me see, let's draw this here together so that we can see it more clearly. Okay, so let's say this is a certain diagonal, and let's say this is another diagonal. Okay, on the polygon. Okay, let's say this is another diagonal maybe, and let's say there is another diagonal from the polygon. So in that case, we will be able to create a triangle inside the polygon such that the vertices of the triangle, they are originally interior intersection points of diagonals, right? And then, yeah, we can see that if you want to have a triangle in this form, so that means that these 2 points, they must lie on the same diagonal. These 2 points, they must lie on the same diagonal, and these 2 points, they must lie on the same diagonal, right? So in that case, it must be of the case like this. So in order to have something like this, we need to select 6 of the original vertices of the polygon so that we pair them up in this particular way so that we form a triangle like this. Okay. On the other hand, so each type of triangle corresponds to 6 endpoints in the original polygon with diagonal drawn in a specific way. But on the other hand, whenever we have 6 vertices selected as from the polygon, then there is exactly one way of drawing the diagonal like this, and then this will always give us a different type of different triangle of this form. So that means what? That means the total number of triangle such that the vertices here are interior intersection of diagonals. There are n choose 6 of them. So this time we have counted another type. So the number of triangles such that all the endpoints here are internal intersection points of diagonals. There are n choose 6 of them. Now we have counted 2 different cases. One is all of them are interior intersection points. And then we have also counted all of them, they are exterior vertex of the original polygon. So we need to count 2 more cases. One is, let's say we have 2 endpoints that are exterior endpoints, and then one of them is the intersection of 2 original diagonals. So in that case, these 2 are a particular endpoints. Yeah, so this is a diagonal, right? So these 2 are on the same diagonal. These 2 vertices are on the same diagonal, and these 2 vertices are on the same diagonal. So in order to get such kind of triangle, we must define what? We must define 4 endpoints here. And whenever we have 4 endpoints, then something interesting happens. Whenever we have 4 endpoints, we will see that it will create 4 kinds of 4 different triangles of this type. So this is one of them. This is another of them. And then this is another one of them. And finally, we have another one. Is that okay? So what does that mean? So that means that for every 4 exterior vertices of the original polygon, we will be able to draw the diagonal in this way such that it will create 4 triangles with 2 endpoints being the original vertex and 1 endpoint being the intersection point of the interior and intersection point of diagonals. So in that case, using the same one-to-one correspondence argument, we will see that the number of triangles of this type, 2 endpoints are original endpoints, and one of them is the interior intersection, is 4 times n choose 4. Is that okay? Now, if you are okay with all the discussion so far, then we can actually compute the last type. So for the last type, what should that be? Okay, so the last type is we need to have, so the last type is like this. We will have one of them are original exterior endpoint, and then 2 of the vertices here are interior intersection. So this is like this. So we want to count how many cases are there for this to occur. Now, we will see that in order to have this kind of triangle, these 2 endpoints must lie on the same diagonal. These 2 must lie on the same diagonal. These 2 must lie on the same diagonal. And then we will see that, and then this endpoint is common. So in that case, we need to define 1, 2, 3, 4, 5 exterior vertices of the original polygon in order to get a triangle like this. But on the other hand, every 5 exterior endpoints, we are going to be drawing the diagonal in this way so that it will create 5 triangles of this form. So we have the endpoints here selected, and then when we draw the diagonals like this, so we are going to create this one, this one, this one, this one, and also this one. There are 5 triangles of the form 1 exterior endpoint and 2 internal intersection will be formed. So every 5 exterior vertices of the original polygon defines 5 triangles of this kind that we are trying to count. So the total number of triangles that we want to count in this case is 5 times, and choose 5. Okay, so in summary, by using rule of thumb, the exact number of this problem will be equal to n choose 3 plus 4 times n choose 4 plus 5 times n choose 5 plus 1 times n choose 6. Okay, yeah, I think that's all for homework 1 today. Yeah, so let me double check if you have any question. So let me see. Okay, so looks like we don't have a lot of question so far. So let's end. So let's end the tutorial today. And then, yeah, two brief reminder. We will have homework 2 deadline set to be next Monday. So that means what? That means that on Tuesday, we will be giving the tutorial about solutions of homework 2. And then also the exam 1 is coming. So exam 1 will be on next Tuesday, next Tuesday. Okay, so the regular class time with 2-hour class time, and then the topics to be covered will be those that are covered in homework 1 and homework 2. So that means we will talk about combinations, permutations, and also the generating functions. Okay, thank you very much. Okay, yeah, that's all for today. Thank you.